Hi everyone. Today we'll be starting a new chapter. It's called functions. So before I start talking about and getting into the actual subject, I just want to tell you, what we're going to be looking at over, this entire period of when we do functions. So functions is probably one of the most important chapters, if not the most important chapters. And the reason is because function is basically branches out into multiple different chapters as well. What I mean is when you have functions, right? We have functions here. So functions branches out into calculus. It branches out into trigonometry. You'll have it in trigonometry and other places as well. So functions is like the cornerstone or the base of other chapters that you're going to be learning on. So I would say that it is vital that you put in the most effort learning functions because it will you're gonna have to use everything you've learned in functions to solve trigonometry. I would say trigonometry, all the questions in trigonometry, whether they come from transformations, whether they ask you to plot sine curves or cosine curves, or even in calculus when you're asked to plot a graph and then draw its derivative, right? You can be given some arbitrary curve in calculus. You're given something like this, and they're saying this is x, this is t, and you have to plot, the velocity time graph of this as well. So it is vital that you understand every single type of function, whether it's a logarithmic function, whether it's the absolute function, whether it's some inequality, parabolas, every single thing, right? Again, I'm going to go step by step. So today is obviously the introduction lecture. We're going to talk about very simple things like relations, functions, domain, codomain, and range. That'll be all for today. Going into the next videos, then we're going to separate them or bifurcate them based on the different type of functions, maybe log functions, um, absolute value functions, and obviously trig functions we'll take a look at when we do trig. So I won't be touching them right now. I won't even be doing any questions right now from them. So as and when we come to trig right after functions, we'll be taking a look at a mix of functions and trig questions. Right, so let's get started with the first thing in functions, right? So the first thing, actually, what we talk about functions is not really functions. It's actually something called a relation. It's probably the first thing in the textbook as well. It's a very small portion in probably the Oxford textbook if you have it, right? So let's talk about relation, right? Relation. Now, honestly, you can skip this part and get on with the main functions, right? I don't need to explain any of this to you. I can directly go to functions, talk about domain, range, and how to plot a function, and be done with it. But I'm giving you a relation just to give you a feel for what's actually happening here, right? So I'm going to start off by talking about relations with multiple examples. That's the only way you can get a good intuitive feeling for what's happening. So suppose we have a set, right? So we have a set basically consists of any arbitrary thing. Like we have a set A and we have a set B, right? Maybe we have, I don't know, arbitrary values. Again, I'll have maybe A, B, C, D, 1, 2, 3, 4, right? So now, as the word suggests, relation, we're trying to find the relation between these two sets. Are these two sets even related? And if so, how are they related? So maybe we say that A is related to 1. A is also related to 3 by some random, thing. Like because I said so, it is, right? In this case. And maybe B is related to 1 and it's also related to 4 maybe, right? And we say C is related to just 2 and D is not related to any of them, right? So I have just, on the spot made up some random relations, and whatever they are, that's how it is, right? So let me give you a better example. Suppose we have another set, right? We have a set A, which talks about, and I'll change the color, so I'll take it orange. Suppose we have set A, and set A is cities, right? Set A is cities, and set B are countries, right? So maybe in set A, I can have New York, so I'll take it in NY. I have Chicago, right? I have Chicago. I have uh, London, right? I have London. I have Sydney, and then I have maybe Mumbai, right? These are cities that I have, and maybe I have countries, the United States. So I'll just put the U.S. So I have the U.S. I have India. I have Germany, and I have maybe South Africa. Right? So this is my set A, which consists of arbitrary cities that I just thought of, on the spot. And this is my set B, which again, arbitrary countries that I thought of. Now, if I have to, create a relation between them, how do I do it? Well, I know New York is a city in the United States, so I can make an arrow right here. That's a relation right there. I know Chicago is in the state of Illinois, which is in the US. I know London, it's in the United Kingdom, but United Kingdom is not listed anywhere on set B, so I don't draw any relation here. Sydney is in Australia, right? Again, not there, so I leave it. I have Mumbai. Mumbai is in India, right? So I have right here. So right, I can have a relation right here. So you can see not all elements, right? Because cities are technically elements of set A. Not all are being plotted onto the elements on set B, right? Some are being left empty, and that's okay, right? That's how it is. That's how it will be, right? Relation is a very arbitrary concept. It's a very broad concept, right? You can mess around with it all you want, right? When we get to functions, it'll change. For now, let's just focus on relations, right? So this is another example of what we would call as relation. Let me give you a few more examples, right? Obviously, not everyone would have understood it, so let's go with another example. So I'll take line this time. So another example, I'll call it example 2 right here. So example 2, I'm gonna go with sports and athletes. Sports and athletes. First one that comes to my mind is Usain Bolt. Oh, sorry, Usain Bolt comes here, right? Usain Bolt. Next one, Michael Jordan, MJ. Michael Jordan. I have Tom Brady, right? I have Cristiano Ronaldo, CR. I have Tiger Woods, right? I'm gonna name it Tiger Woods as TW. I have Lewis Hamilton, right? And maybe one more, Virat Kohli, right? Like this. Now I have sports. I have maybe curling. I have chess, right? Although a lot of you may argue, but let's leave it here. Like, I call chess as a sport, even if you don't, I know some people are watching this video and be like, oh, yo, chess is not a sport. Whatever. I say it is. For now, let's keep it as it is, right? I have football. So this is American football. So American football. I have soccer. I have cricket and baseball. Right? These are my elements in my set A, right? Again, this is set A, sports is set A, and athletes is set B, right? So curling, right? Any sport, right? Is there any correspondence to any athlete here from curling? No. So we just leave it as it is. Chess, is there any correspondence? No. American football, yes, there is. There's Tom Brady. We have Tom Brady right here. That corresponds with American football. We have soccer. Yes, we do. We have Cristiano Ronaldo, right? We have Ronaldo right here. Cricket, yes, we do. We have Virat Kohli, right? There's another one. Baseball, is there any baseball player here? No, there isn't, right? Usain Bolt, he's a track athlete, right? Runner. Michael Jordan, basketball player. Tiger Woods, golfer. Lewis Hamilton, F1, right? Formula One, right? So as you can see, again, we have certain things that go to certain players, right? Some there is not relation between, there need not be a relation between every single element from both sets, right? Curling, there is no relation. Usain Bolt, there is no relation. All right, that's okay, not an issue, right? Again, I just want to give you the feel that relation is a very arbitrary concept, and you can take it to be whatever you want, right? As long as you're able to draw something from another, right? Obviously, if maybe American football, soccer, and cricket were in there, then we basically have technically no relation between those two, both sets. That's okay also, right? Let me give you one final example, and this is probably my favorite because it stuck with me the most, and it's something that I know. I don't remember where I got it from, but I do remember learning it somewhere when I was in school. So this is if you have ever watched Bollywood, it's probably from there, right? So let me put in male celebrities here. So male celebs and female celebs, right? So I have Ranbir Kapoor here. Okay, Ranbir Kapoor. I have Ranveer Singh, right? Don't mix their names up. So Ranveer Singh, and I have a badminton player, Prakash Padukone. Prakash Padukone. Right here, female celebs. I have another actress, Alia Bhatt, and I have Deepika Padukone. Now, those who have watched Bollywood, right, who know Bollywood, who know Indian celebs, right, they can immediately draw, you know, I guess, a relation between them, right? So we know Ranbir Kapoor, right now, currently, is Alia Bhatt's husband, right? They're married. We also know that these two were in a relationship, right? Ranbir Kapoor and Deepika Padukone are exes. But we also know that Ranveer Singh and Deepika Padukone are husband wives. And we also know that Prakash Padukone is the father of Deepika Padukone, right? So now we have two sets, right? Male celebs, female celebs. So now here what happened is I was able to draw a relation between every single element from the male celebs to just one element, right? So Deepika Padukone is internally related technically, or non-technically if you want it, is technically related, or has or had a relation with all three of them, right? Where Alia Bhatt just has one, that's okay, right? But Ranbir Kapoor had two, Deepika Padukone has three, right? So this is the what I'm trying to give you a feel like. This is probably the best way I can give you a feel. If you know Bollywood, take it like this. If you don't, maybe you can think of it like maybe Justin Bieber and Selena Gomez. It's kind of old, I guess. I'm not too sure, but yeah, you can use that as an example. Also, you can make a similar chart like this with celebs and male celebs and female celebs, and draw arrows like this, making a relation. Like technically, you're making a relation, right? So here again, the relation is that Ranbir Kapoor, Deepika Padukone, Ranveer Singh, Deepika Padukone, Prakash Padukone, Deepika Padukone. That is the relation that's being drawn here, right? So again, let me how, if I had to list out the relation, we can say that they're married, exes, and married, and father daughter, right? So this is the prime example that has always been stuck with my brain, right? I don't remember where I got it from, but I remember watching something or someone told me about this, and ever since then it's been stuck, right? I mean, it's a pretty silly example, to be honest, but it's often those silly examples that stick with you, and this is why I never forget when someone talks about relation, right? This is the first thing that comes to my mind. Oh yeah, now then I draw a conclusion with this, right? Okay, so this is happening here, this is going here, this is going here, and all stuff like that, right? So again, this is essentially what relation is, right? This is all you need to know. Like I said before in the beginning of the video, even if I skipped this part, it would have been fine. You could have still, if I just directly went to functions, you could have done that. But for the sake of cohesiveness, I guess the text, I'm kind of following the textbook in this way, that it just gave you a brief explanation of what relation is, and now we can move to functions, right? So let's look at functions now, starting with functions now. This is the main part. So again, if I have to give the textbook definition, it would go something like this. A function is a special case of a relation, right? It's a special case of a relation where every element of the first set, also known as the domain, right? I'll get into the terminologies later. First set, which is the domain, right? Has only one output in the second set. In the second set, okay? And the second set is known as the codomain, right? like this. Again, let me explain with an example, right? I'll take peach, right? So let me draw a set A here, right? I'll do it here so you can actually see the definition as we talk, right? So we have, all right, let me redraw this. Let me draw an ellipse so I can put in all the elements, something like this, right? And I have A, and then I have B, right? Like this, right? So in this, I have, A, B, C, D, and I have 1, 2, 3, 4. So now let me just draw some random relations, right? Some arbitrary relations here. So I can say maybe A corresponds to 2, or it has a relationship with 2. B corresponds with 1, like this. And then C corresponds with 4, like this. So now the definition says it's a special case of a relation, right? We have a relation here, but a function is a special case, right? It has to meet certain requirements. And there are two requirements, right? The first requirement is right here. Is every element, basically, every element has only one and only one output in the second set, right? One and only one, right? Has only one and only one. So something like this. Has one and only one output in the second case, right? So the condition is that there should be, only one output. So A can only have one output. It can only lead to one element in this, right? And the second is that all elements, should have a final output. So what I mean is, okay, let's look at this one by one, right? So we have A. A corresponds to only one element, so that's check. That's good. B corresponds to one element. That's also good. Perfect. Fine. C corresponds to one element in set B. Perfect. But D corresponds to absolutely no element in set B. So take it like this. Suppose we put in something in the calculator like 2 plus 2, right? 2 plus 2. You type 2 plus 2 in the calculator and you get 4. Now you press 2 plus 2 again in the calculator, and you get 5, right? So basically what's happening is you're getting two values, right? So 2 plus 2, the calculator gives you 4 first, and then it gives you 5. So now you have two possible values for 2 plus 2, right? Which is not possible, right? So now we only need one definite value, right? That's what matters. And again, we're only focused on set A, right? Focus on set A, which is our domain, right? Our domain, right? This is our domain. That's what matters. We don't care about what's happening with set B. We only care about what's happening with set A. So, like I said, now if we had maybe, for example, A also corresponds to 3, like this. So that's essentially saying 2 plus 2 gives us 4 once and it gives us 5, right? How is this possible? It's not. Therefore, this relation right here would not be a function, right? Another reason, for example, let me say if I put 3 plus 3, right? 3 plus 3 is 6. We all know that. But if I put 3 plus 3 in the calculator and it gives me absolutely nothing, maybe it puts an error, or the screen goes blank, right? It's absolutely blank, like nothing is out here, right? There is no value corresponding to set B right here. So because there's no output for the specific input, right, we can't call it a function, right? So again, if you want me to list out basically the two conditions, right? So I'll do it right here, right? So first condition is our input must have only one output, right? 2 plus 2, that same example. You can always use that, right? And the second one is that every input must have an output, right? Or in this case, basically, every domain must have a final value, right? Which it corresponds to. This is the codomain, right? The set B is the codomain, right? So again, now if we had to rectify this, right, one way we could do is maybe take out this relation right here. So now we fix the relationship again with A. So A only corresponds to 2. That's perfect. B corresponds to only 1. That's perfect. C corresponds to 4. No problem. Now, if we make a relation right here, and if I say now that D corresponds to 3, so now we have a function, because again, every single input has an output, and every input has only one output, right? These are the two conditions that we had to meet, and we're meeting them. Hence, we can call this relation is a function, right? So this relation is now a function. So now that we have explicitly seen the difference between a function and a relation, let's look at some key terminologies right here. So the key terminologies in this are domain, codomain, and range. Okay, so let me change the color again. Let's make it purple. So we have domain, codomain, and range, like this. So let's talk about, I'll change the color again, bring yellow. So we have something like the input, right? The input, now put it as X, right? And this is also known as the pre-image, right? Pre-image, what I'm putting into the function, right? Maybe I have -2, -1, 0, 1, and 2, right? This is my input values, right? And then I have my output right here, output as Y, right? So that's my image, no issues, right? So I would have maybe 0, 1, 2, 3, 4, like this. Oh, my bad. Let me redraw the ellipse, like this, right? So again, I'll name this as domain, and I'll explain the difference between codomain and range just in a second. So now let's define a function. Maybe the function that we define is y is equal to f of x, right? So function is f of x, and it corresponds to basically y, right? So and f of x is equal to, so I'll do it like this. So y is equal to f of x, and f of x is equal to x squared, right? So whatever values of x we have, we square them, and that becomes our y, right? Again, a very simple thing. You've probably heard of this, in 9th grade or 10th grade, called the an upwards facing parabola, right? So now if we have to plot an image of every single pre-images, so what do we have, right? We'll have for -2 whole squared corresponds to 4, right? -1 whole squared corresponds to 1. 0 corresponds to 0. 1 squared corresponds to 1. And 2 squared corresponds to 4. Like this. Right? So now we have our outputs, right, for the specific inputs. Now, if you're still confused about the definition of function, let me explain again, right? We're only focused on this, right? Focus is here, right? We don't care about what's happening here. What was the condition? That every single input must have an output, right? And every input must correspond to a different output, right? So basically, your input can't have two outputs. So right, -2 corresponds to 4 only. It doesn't correspond to 3 and 4. It only corresponds to 4. So it's okay. Similarly, -1 corresponds to only to 1. Doesn't correspond to 0 or 2 or 3 or 4. That's fine. 0 corresponds to what? It only corresponds to 0, right? Doesn't correspond to any other values. 1 corresponds to 1. Similarly, 2 corresponds to 4, right? Now you must be thinking, wait, hold up. 1 corresponds to here, -2 and 0. But then I told you, ignore this. We don't care what's happening with this. We ignore this and we focus on this. As long as the conditions meet in the domain, that's all that matters. We don't care whether 2 and 3, 2 and 3, don't correspond to anything right here. That's okay. It doesn't matter. We don't care, right? We only care about this. Now, for example, if this was the other way around, maybe if this was a domain and this was our range or codomain, whatever, our input, if this was our input, right? Let me highlight it. If this was input and this was output, right? Then it would be a problem because two inputs go to basically one input corresponds to two different outputs. That would be an issue, but it doesn't matter in this case. So this is why we can call it a function, right? Now let's talk about codomain and range. So basically, this is set B, right? And everything, all the values, 0, 1, 2, 3, 4, are part of the codomain. So what is the range then? Range are only the values that are mapped from the domain. So range here in this case, the only values in the range are 0, 1, and 4. That's it. So range you can think is like a subset of the codomain. Codomain is the big umbrella, and range are the small elements that fit in it, right? The range not doesn't necessarily need to fulfill every single element of the codomain, right? It can, doesn't need to, but the range here is just 0, 1, all the values that have been mapped from the domain, right? I hope this clears up the confusion between domain and range codomain. Sorry. So now let's look at just a few examples of functions and whether it's a function or a relation or just a relation and not a function. All right, so let's look at the first example. Pause the video, try it on your own, and then come back for the answer. So now the first one is a function, and I'll explain how. So first condition is every element right here, right? 1, 2, and 3 has an output, right? And each output has only one. So each input basically has one output, right? So 1 only goes to y. It doesn't go to x or z. 2 only goes to y, right? Regardless of the fact that both corresponds to y, that's okay. Think of it, being, something like this. So if we put, 3 times 0 in the calculator, right? We're going to get 0. Whether it's 2 times 0 or 3 times 0, we're going to get 0 for both of them, right? So think of the scenarios like that, right? You do get an output, right? And then we have 3 that only corresponds to z, right? So every input has one output, one specific output, and every input has an output in general. So it meets the two conditions, right? Condition 1 is met, and so is condition 2. So this is good. Let's look at the next one. Now, next one is a relation, but it's not a function. Right? Now, it's basically because the first condition is not met, right? Not 1 and 2 have an output, but 3 doesn't have an output, right? 3, there is no output, right? It's like saying putting in 3 times 0 and getting a blank value in the calculator, right? You're getting a blank screen. Like, you're supposed to get 0, but you're not, right? You did 1 times 0, you're getting 0. You're doing 2 times 0, you're getting 0. But you're doing 3 times 0, you're getting a blank screen. Like, how is that possible, right? So this is why it's not a relation, right? The other condition, you can't even really talk about it because the first condition itself has failed, right? So let's look at the final example. So we have 1 corresponds to x, right? 2 corresponds to y and corresponds to z. So it's a relation, but it's not a function, right? Relation, but not a function, like this. So again, because of the fact that 2 has 2 possible outputs, it's like putting doing 2 plus 2 and getting 4 as one answer and 5 the next time you do it in the calculator again, right? You can't have that. This is why this is not a function, right? 1 corresponds to x, that's perfectly fine. 2 corresponds to 2 outputs, one input corresponds to 2 outputs, that's not possible. This is why this is a relation but not a function. So now let's look at a graph of a function, right? So again, a function can only be graphed once you have a specific, defined function. So in this case, we have f of x is equal to x squared, right? And we know y is equal to f of x, right? Because it's the output, so it's always going to be plotted on the y-axis, and the input is always plotted on the x-axis. All right, so let's take in some x values. So we have some input, and then we can put in, and then we can plot the corresponding y values. So maybe if I have x and y right here, so maybe I have -2, -1, 0, 1, 2. I'm taking a very standard example just to keep it as clean as possible. So 2 squared is 4, 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So if I have to plot this, right, I'll change the color. So something like this. So 0, 0, 0 would be right here. So 0, 0 would be here. 1, 1 maybe would be somewhere right here, and minus 1 comma 1 would be like right here, 2 comma 4 maybe would be somewhere right here, and then minus 2 comma 4 would be right here. So essentially this would look like a parabola. Please forgive me, it's not that great, but you get what I'm trying to do here, right? Let me see if I can draw this again one more time. So something like this, right? It's not very great, but like this, right? I'm gonna try adjusting it now, like this, and then so about this much, right? Like this. So you're gonna have something like this, right? And this is what happens after you plot it, right? It's a very simple x coordinate, y coordinate game, right? You're not doing anything rocket science here. You're just plugging in the values, plugging in using the formula or using the function and putting in the x value and getting a corresponding f of x or y value, right? Now, one more way which we can test out whether following relation is a function or not, or a function is actually a function or not, is by the vertical line test. Okay, so let me take another example. Let me take a fresh page and I'll make a new title. So keep it in light blue and I'll call it the vertical line test, right? Vertical line test. Okay, so this is basically to check whether a curve or a graph is a function. Is a function, right? So again, I'll take two examples here. So the first example I'll plot is something like a normal parabola, right? Which I did previously. So I have something like this, right? And then take yellow. So I'll do like this, right? Put it right here, right? A normal, simple parabola, like this, right? Like that. So what I do in this case is I'll take red. What I'm going to do is I'm just going to draw a vertical line, right? Through the graph, anywhere, right? Whether it's here, like this, whether it's maybe right through the center, doesn't matter. So what I'm going to look for is the intersection between the red and the yellow line, basically the vertical line that I drew and the curve itself. So I'll take another color here. Take blue. Oh, yeah. I'll take blue. So there's an intersection point here. There's an intersection point here, right? So what we're looking for is basically there should be one intersection per red line, right? Per vertical line, there should be one intersection, right? So as you can see, there's only one intersection here. So that's all good. There's only one intersection here. That's all good. So basically, if you have, now if I have to define this, right? For it to be a function, for it to be a function, there must be only one intersection point, right? Which means, and we can also say that it's past the vertical line test, and it's a function, right? We can claim this curve to be a function, right? We can claim that a parabola or any parabola in the form y is equal to x squared is a parabola, is a function. Now let's take another example, right? So maybe I have a function like y squared is equal to x, right? The first one was y equal to x squared. Now I'll have y squared is equal to x. It's kind of like the opposite. So in this curve, I'll just give it to you, right? So again, it's going to be something like this. It's a sideways parabola, like this, like this. So like this, right? Now if I draw a red line, right, or a vertical line, like right through here, like perfect, like right smack down the middle. So now what I notice is I have two intersection points. One is right here and one is right here. And because there are two intersection points, it fails the vertical line test. Because there are two intersection points, it fails the vertical line test. Okay, that's the thing. So now again, if we correspond to this original definition where we had those sets, those ellipses that I drew, and making lines from one set to another set, think of it this way, right? Basically, for this value of x, right, this specific value of x, we have two y values, right? Maybe we can call this y1, y sub 1, and we can call this y sub 2. So technically, we have two values, x, comma, y sub 1, and x, comma, y sub 2. So think of it this way. Maybe we have 1x in set A, and then we have y1 and y2 here. So we have basically like this. Let me change the color again. So we have, maybe I'll take pink right here. So we have something like this, right? We have this and we have this. So, and this was the definition which I previously said, that this makes it not a function, right? This is why it's not a function. So this is the same thing, but it's in a graphical representation. That's all I've done, right? That's all I have done, nothing else, right? So this is how you can determine whether a curve or a graph is a function or not, through the vertical line test. Okay. There's also another thing called the horizontal line test, but that comes in later, and it's much different. Okay, so now let's talk about domain and range. Again, domain and range, just gonna go over the surface level, right? I'm gonna go it's like the icing of the cake. I'm just gonna explain that, because there will be certain specifications with respect to every function we study, right? So when we study the log function, we're gonna have something. When we study the absolute, we're gonna have something, right? So for now, I'm gonna give a general overview of what a domain and what a range is, right? So domain, right? So right here. So we have a domain, right? So domain is just the input values. Or if I have to make it more specific, I can call it all acceptable input values. All acceptable input values. Input values for the specific function. Right? So what I mean by this is, suppose if I have a rational function, maybe, right? If I have a rational function, right? A rational function is basically f of x is equal to 1 upon x. Okay? And if you plot this, you have a graph something like this. You can plot it in your TI-84 if you have it, or you can go on Desmos and plot it. You'll have a curve something like this, right? Where the axes are like this. And so you could basically have a rectangular hyperbola. Again, if that makes what I just said makes no sense, forget it, right? So now this function exists for all values except x naught. So the domain is all values. So x belongs to all real numbers, but x does not belong to 0. Because what happens at 0 is that if we put 0 for x, we're going to have 1 upon 0. And 1 upon 0 is infinity, or in more technical terms, it's undefined. So if we don't have a definite output, we can't call it a function, right? So hence, to call this at 1 upon x a function, we restrict the domain, right? And we only take in the acceptable values to make it a function, right? Similarly, if I have one more, maybe square root function, right? So this was the first example. Let me go back a circle. So this was the first example, and maybe if I have something like the square root function, or I'll use a different color altogether. So I'll take line. So I'll have square root function. Okay. Again, example here would be f of x is equal to the square root of x. So here, and this graph, comes out to be like this. So it'll be like starting from the origin, it'll go out like this, like that. Okay. So the domain here has to be that x is greater than equal to 0, right? x has to be greater than or equal to 0. It can't have any negative numbers, because the square root of negative number, basically that results in complex numbers, like we discussed before in the complex numbers chapter, right? Again, they're not, we're only talking about real numbers here, so we're not talking about imaginary numbers. So the domain here has to be x is greater than or equal to 0. Otherwise, this function will not hold, right? You can't have any acceptable values. So again, we adjust the domain so it meets the criteria of the function. So it works, right? In the end, it has to work, and it works by basically, again, it works by basically by putting in acceptable values. So if I have to give you guys a small, quick example of domains, right? So I can take very simple examples. So one example, will be, so let me change the color. So maybe an example can be like this. We have basically find the domain of f of x is equal to 2x upon x squared minus 4. Okay, x squared minus 4. Like this. It's a rational function. When we get into it, I'll explain it more. So I know that basically the numerator can be 0 anytime. Doesn't matter. But the denominator cannot be 0, right? Because if you have something upon 0, it's undefined, hence no acceptable value. So basically the x is valid everywhere except for when the denominator is 0. So when the denominator is 0, so x minus 4 is equal to 0. When x is equal to plus or minus 2. So basically we can say that the domain belongs to all real numbers except for minus 2 and 2. So this is like the proper way of writing it, right? So domain like this. X belongs to all real numbers, and take out minus 2 and 2 from that, and you have your domain, right? So this function will have or will produce an output, right? All values except minus 2 and 2, because you have 0 in the denominator, right? You can look at multiple examples later on. I'm just going to give you one for now, because we're going to get into specific functions later on, right? So now let's look at range. Okay, so range is right here. So we have range. So basically range, again, by textbook definition, is the set, and I've defined range before, right? When I was talking about codomain and domain and range, right? It's the same thing, right? Set of values of or set of values of y, right? Y obtained by using all possible values of x as input. All possible values of x as input. Okay, so again, I'm not gonna, again, if you use the same example here, right? So this example, if we talk about, what would be the range of this thing, right? Well, if you think about it, this is kind of, a hyperbola. Or you know what? Let me use a simple example. This can get a little, hairy and complicated for now if you have never studied, rational functions. So if we have, for example, f of x is equal to x squared, and I drew the function as well, right? So I know x squared will basically consist of all you square anything, you're gonna have positive values, right? And the lowest you can go is 0, right? And the highest you can go, well, you can go to infinity. So the range here is 0 to infinity, right? So this is the range of this function, and you can always check it by plotting the graph itself like this, right? And now let me explain one more thing right here, which I did. So here I used a square bracket, and here I used a parentheses. So parentheses means it doesn't include, right? So again, I'll change and I'll write the convention here. So when I have this, it means includes, and you can use this for domain as well, and this means doesn't include. So let me rewrite this. So doesn't include. Okay, now Zero obviously touches it, so it includes. Now, for infinity, we always have parentheses because infinity means it's an undefined value, and we don't know where it goes up to, right? So that's why we always do for infinity. We always put a parenthesis sign. Always remember that, right? You can have maybe two and infinity like this. You can have maybe minus infinity and five like this. It doesn't matter, right? This is all acceptable. We can't have a square bracket or a square, yeah, basically a square bracket for infinity, whether it's minus infinity or plus infinity, right? Just want to make sure that's clear with everyone in the notations. I'm sure your teachers must have gone over it. It's just a small thing, as a reminder that I've put in. Okay, so this sums up and this wraps up today's video. So I didn't want to make it too long because it can get a little confusing. But like I said before, functions is a very important chapter, right? You're gonna have a lot of small nitty gritty things that you need to be careful of. Okay, go over this video, and I'm gonna put the notes in the description, so you can hit the link in the notes in the description, and it will direct you to a Google Drive PDF of whatever I just explained here. Right? You can go over it, revise over it. Next video, we'll take a look at specific functions. I don't know from where I'm going to start, but I will. Which functions I'm going to take, but that'll be, I'll decide that later on. So yeah, again, just revise this. If it's a little confusing, watch the video again. Look at the textbook. Maybe the textbook can also help you, and do the small exercises from the Oxford textbook if you're using that, or any textbook. Right? I'm not going to go over every single textbook example because you have the solutions, you have the answers. You can always work on them. I'm always going to I'm going to focus on the special cases or the examples which I feel that are exam style questions that will come later on. Okay, so do the questions of the textbook, try it out, and I'll see you in the next one. Bye bye.